Good morning. This is Engineering Statistics and Linear Algebra 18 EC 44, Module 4, Lecture 7, the four fundamental subspaces. So let us see the basics of subspaces which we have considered till now. We can describe the subspaces in two different ways. Firstly, we can say that a set of vectors that span a space. A subspace is just a set of vectors that span the space. For example, the columns span the column space. This description may include useless vectors, and that useless vectors will be the dependent columns. The second description of the subspace is we may be told which condition the vector in the space must satisfy. So we have seen that whenever, what should be the values of B for which the AX equal to B has a solution. And that the example for that is the null space consists of all vectors that satisfy AX equal to 0. So this description may include repeated conditions, which is the dependent rows. So in the first definition, we have dependent columns. Here we have the dependent rows. So when the rank is as large as possible, that is R is equal to n, then the matrix is supposed to be having a left inverse. And if the rank is as large as R equal to m, then we call that as we can have a right inverse C. And if R is equal to m equal to n, and that will be a square invertible matrix, then we have the two-sided A inverse. So till now we have considered two subspaces, that is the column space and the null space. But still we are left with the other two subspaces. So on the whole, we can say that there are the four subspaces. The first one, the column space, which we already studied, is denoted by CA, and its dimension is the rank R, which we already seen. The null space of A is denoted by NA. Its dimension is n minus R, associated with the free variables. This is concerned with the pivot variables. The third one is the row space of A is the column space of A transpose. The row space of A is the column space of A transpose denoted by C of AT, and it's spanned by the rows of A. Because we're taking the transpose, it's spanned by the rows of A. Its dimension is also R. So the dimension of the row space as well as the column space is same, R. The left null space of A is the last of the four subspaces, and it is denoted, it is a null space of AT, A transpose. That's why we call this as a left null space. It contains all vectors y such that ATY is equal to 0. That is, the A transpose of y is equal to 0, and it's denoted by n of AT. Its dimension is m minus R. Once we take the transpose of A, then the number of rows and the number of columns will get exchanged, and hence the dimension will just turn out to be m minus R, compared to the dimension of the null space, which is n minus R. So the null space NA and the row space C of AT are both subspaces of Rn. They have the dimension which is n. The left null space n of AT and the column space of CA are the subspaces of Rm. Let us take an example of the four subspace. An example is A is equal to U is equal to R is equal to 1, 0, 0, 0, 0, 0, as shown in this value here. So the column space is the line which is passing through 1, 0, because the others are 0, 0 over here. We have three columns, and only this is the column which is having the pivot variable, and therefore the column space is the line through only this 1 and 0, others are 0, 0, hence they don't contribute anything there. The row space is the line through 1, 0, 0 transpose, and it is in R3. So the row space, the way in which the row space is to be considered is 1, 0, 0 over here. The rows which are having non-zero, and this is 1, 0, 0. This 0, 0 does not contribute anything because it is a 0 vector. This 1, 0, 0 will just give us that, and that transposed will give us the row space. The null space is a plane in R3, and the left null space is a line in R2. So NA contains 0, 1, 0 and 0, 0, 1, 0, 1, 0 and 0, 0, 1 other than 1, 0, 0 in the identity matrix, and NAT contains the 0, 1 other than the 1, 0 in the identity matrix, which is 2 by 2. Here we consider the identity matrix, which is 3 by 3, and here we consider the identity matrix, which is 2 by 2. All the 4 vectors are the column vectors, because here you can see that this is a column vector, and once we take the transpose of this, it becomes a column vector, and this is also a column vector, and this is also a column vector. Now you can have here a null space vector matrix which consists of 0, 1, 0 and 0, 0, 1 as its 2 columns, which we generally call it as N. Na is the null space itself, which contains the what you call the columns over here. The detailed description of the 4 subspaces is specified here. First, let us consider the row space of A. For every U and R, U is the echelon matrix and R is the reduced row echelon form. The non-zero rows are the basis. Leaving the 0 rows, if we take the non-zero rows, they form the basis, and the row space has the dimension R. This we already considered. The row space of A has the same dimension R as the row space of U. You can see that the row space of A as well as the row space of U are having the same dimension R, and it has the same basis because the row space of A, U and R are the same. We have the row space of A, U and R same, and hence the dimension is same for all the 3 things, which is R. The next one is the null space of A. The null space of A is same as the null space of U and R again. The null space Na has dimension n minus r. The special solutions are the basis for this, where we consider each free variable is given a value 1, and the other free variables are made 0, and then we can try to solve Ax equal to 0, Ux equal to 0, or Rx equal to 0, any one of the 3, and that gives us the pivot variables by bag substitution. The null space is also called the kernel of A. We give a new name for the null space, which is known as the kernel of A, and its dimension is n minus r, which is generally called as the nullity. The column space is the one which we have considered in detail till now. The pivot columns of A are the basis of its column space. So A might have pivot columns as well as free columns, and the pivot columns will form the basis for the column space. The dimension of the column space CA equals the rank R, because it corresponds to the pivot variables. The number of pivot variables is naturally equal to the rank, which also equals the dimension of the row space. The number of independent columns equals the number of independent rows. Always we see that the number of independent columns and the number of independent rows are same. A basis for CA is formed by R columns of A that corresponds to U to the columns containing pivots. So row rank is equal to the column rank, that's what is specified over here. The number of independent columns equals to the number of independent rows, so that will give us the row rank equal to column rank. If the rows of the square matrix are linearly independent, then so are the columns. and vice versa. So if we have the rows of the square matrix linearly independent, then the columns of the what you call matrix will also be linearly independent, and the inverse also applies there. The left null space of A is the last of the four subspaces, and that is generally the null space of A transpose. For any matrix, the number of paired variables plus the number of free variables must match the number of columns. We've seen that, if we reduce a matrix A, then we will get some of the pivot columns and some of the free columns. The pivot columns will give us the pivot variables, and the free columns will give us the free variables. The sum of the pivot columns and the free columns will become the total number of columns. So in other words, the rank plus the nullity, which is generally known as the rank nullity theorem or dimensionality theorem, equals M. And that is specified over here as dimension of CA plus dimension of NA is equal to the number of columns. The left null space, N of AT, has the dimension which is M minus R. So this just gives us the four different dimensions. This figure gives us the four different dimensions and four different fundamental subspaces with their dimensions and different things. So here you can see that this just corresponds to the what we call r to the power r to the power n space, and this corresponds to the r to the power m space. What it means is that the row space as well as the null space are within are the subspaces of Rn, and column space and left null space are the subspaces of Rm. And the row space has dimension r, the null space has dimension n minus r, the column space has dimension r again, and the left null space has dimension m minus r. So the way in which we can specify that is the column spaces of ax is what we will have here, and the row spaces of aty will be there over here, and the null space is ax equal to 0. The solution for ax equal to 0, left null space is got by finding the solution for aty is equal to 0. The what we call symbols for the different things, that is this is the row space, which we generally call it as C of AT, and this is C of A, which is the column space of A. This is specified by null space of A, NA, and this is the null subspace NAT. So the row space and the null space are so to say orthogonal to each other, and the column space and the left null space are orthogonal to each other. Now we come to the what is known as fundamental theorem of linear algebra, which we already considered, and this is the fundamental theorem of linear algebra part 1, where we specify four different quantities, where the column space of A has the dimension R, null space of A has the dimension n minus R, row space of A has the dimension R again, and the left null space of A has the dimension m minus R. Let us consider an example of the four subspaces. We'll try to find out for a matrix what are the four different subspace values. So here we are considering A is equal to 1, 3, 2, 6, M is equal to N equal to 2. The rank is 1 because of the reason that the second column is the multiple of the first column. If you multiply 2 with the value 1, and you'll get 2. Again, if you multiply 2 with the value 3, you'll get 6. Similarly, the rows also are dependent. If you multiply 3 with 1, you'll get 3. If you multiply 3 with 2, you'll get 6. So the rows are also dependent, the columns also are dependent, hence the rank on the whole is equal to 1. The column space contains all multiples of 1, 3. The reason being that the second column is in the same direction and contributes nothing new, because it's just a multiple of the second column is a multiple of the first one, and hence the second column does not contribute anything new, and it's in the same direction as the what we call column 1. The null space contains all multiples of -2, 1, and this is the one which satisfies the condition Ax equal to 0. We can find this by just considering, Ax equal to 0, that is this multiplied by this. That is the solution for Ax equal to 0 will give us the null space. If you multiply this with this, we are going to get a what we call 0 vector, a 0 vector. The row space contains all multiples of 1 and 1, 2. This is a column vector, since strictly speaking it is in the column space of 80. So so to say, the row space is just column space of 80. You take the transpose of this, then it will become 1, 1, 2 over here, and 3, 6 over here, and then naturally the row space will just correspond to 1, 2 taken transpose, that will become 1, 2 coming in the column format or column vector format. The left null space contains all multiples of -3, 1, and left null space, we know it is n of A transpose. That means you take the transpose of this, and then A transpose y is equal to 0. You take that and take this, you need to find the solution for that, and naturally the transpose of this multiplied by this is going to give us the null vector, which is 0. So this figure specifies to us in the example, whatever we have written there, the what you call line which is going through this. This is the what you call different lines. This is one line, and this is one line, and this is one line, and this is one line over here. The column space CA is specified as the multiple of 1, 3, and which will correspond to this line. This is the 1, 3, which is corresponding to the multiples of what you call the column space, column space, which is multiple of 1, 3, and that is falling on this particular line, and this corresponds to the column space for that example. And this will give us the perpendicular or orthogonal to this line, and that gives us multiples of 3 and -1. Similarly, if you see over here, the null space in A is what you call this, with the values to -1, and the row space is the column space of the A transpose, and you have this A, and A transpose will give us 1, 2, the column space of 1, 2 here, and 3, 6 here, and the column space of this will just correspond to multiple of 1, 2, and that is the line which is passing through what you call 0 over here, and the point which is 1, 2 over here, and this will be definitely perpendicular to the null space, which is NA, which just corresponds to 2 and -1. With this, we come to the end of the lecture 7. We will be going to the lecture 8 in the next class, which corresponds to linear transform. We might go for additional video for finding out the what is known as left inverse and right inverse of the matrices. Thank you.